Welcome to Biogas Basics. My name is Jürgen Kube, and today's presentation is about the standard academic model of the biogas process, the anaerobic digestion model 1, in short ADM1. For the uninitiated, the ADM1 looks complicated, but one of its greatest benefits is that it can explain a lot about the biogas process. I will ignore the maths and formulae and focus on the symbiotic network that makes the biogas process work. Let's dive straight in. Before I start with the ADM1 model, I will quickly show the overview of the AD process. If you watch this video, this should not be new to you, and I show it mostly for the color schedule I will use in the following slides. The standard explanation in textbooks is that the biogas process operates in 4 stages: hydrolysis, acidogenesis, acetogenesis, and methanogenesis. In the ADM1 model, a disintegration step precedes the hydrolysis step, in which the composite feedstock disintegrates into soluble and particulate inerts, carbohydrates, proteins, and lipids. I'm not a great fan of the 4-stage explanation. First, hydrolysis and acetogenesis are catalyzed by the same group of microorganisms and should be considered as one stage. Secondly, this stage model creates the illusion that the 4 stages run consecutively. Sometimes AD plants try to simulate this behavior with a cascade of reactors with different pH and temperature, attempting to create optimal conditions for individual stages. I will make a presentation about hydrolysis plants in the future, where we investigate external hydrolysis stages in more detail. The reality is that all these stages operate in a strong symbiosis and simultaneously, as this presentation will show. The hydrolysis step is highlighted in blue. Biopolymers are broken down by extracellular enzymes into oligomers, and the oligomers are transported over the cell walls of acidogens, which ferment those oligomers to hydrogen, CO2, and volatile fatty acids. The production of oligomers is energetically more favorable than the production of monomers, but in the terminology of the ADM1 model, carbohydrates break down to monosaccharides, proteins break down to amino acids, and lipids to long-chain fatty acids. I use the terminology of the ADM1 here and limit the reactions to the excerpt that is in the original ADM1 publication. In the ADM1, the hydrolysis reaction rate is not correlated to the concentration of acidogens. It is a pseudo-first-order reaction. Reaction steps in the acetogenic stage are highlighted in green. The acidogens comprise sugar degraders, amino acid degraders, and long-chain fatty acids degraders. They produce hydrogen, CO2, and volatile fatty acids ranging from acetic acid to valeric acid. Higher volatile fatty acids are fed to the acetogens, which comprise propionic degraders and a combined group of valeric and butyrate degraders. They produce hydrogen, CO2, propionic acid, and acetic acid. Acetogenic steps are marked in orange. Acetic acid is consumed by acetoclastic methanogens, and hydrogen and CO2 are consumed by hydrogenotrophic methanogens. Methanogenic reactions are highlighted in gray. The first step in the ADM1 is the disintegration. The composite feedstock degrades to soluble and particulate inerts, carbohydrates, proteins, and lipids. Soluble components are marked with a thin, particulate components with a bold, and gaseous components with a dashed border. Carbohydrates, proteins, and lipids are particulates. Disintegration is considered a purely physical, mechanical, or thermal decay reaction. The disintegration is modeled as a first-order reaction. The reaction constant can be set to a high value so that the disintegration becomes irrelevant, and the following hydrolysis reactions become rate-limiting. I will discuss this later. The first hydrolysis reaction is the conversion of carbohydrates to monosaccharides. The ADM1 does not distinguish between cellulose, starch, or hemicellulose, even though these different carbohydrates have different reaction rates. The reaction is a first-order reaction and does not take any microbial biomass concentration or enzymatic activity into account. The model assumption is that enough glucosidases such as amylases and cellulases are around, and that their activity is constant and not dependent on the biomass concentration of acidogens. Because hydrolysis and acidogenesis are linked, I discuss the 2 phases together for each substrate fraction. Generally, acidogenic bacteria are often facultative anaerobes, meaning that they can grow in the presence of oxygen using respiration and in the absence of oxygen using fermentation. Respiration generates far more energy in the form of adenosine triphosphate, or ATP, than fermentation, making respiration the preferable catabolic pathway. This makes acidogens very effective oxygen scavengers in the biogas reactor. Even if some oxygen is in the gas phase or sparged into the digestate in the reactor, all oxygen that manages to dissolve in the liquid phase is immediately consumed by respiration, making the bulk of the liquid in the digester oxygen-free. Some acidogens and acetogens can also use sulfate and nitrate as terminal electron acceptors. However, respiration reactions are not in the ADM1. Nature has developed many different fermentation reactions, but not all reactions are equally favorable. The most favorable reactions create the most energy in the form of ATP. I have listed some of the most common fermentation reactions from glucose below in the order of energy produced. The highest energy yield comes from mixed acid fermentation, creating acetic acid, hydrogen, and CO2. This pathway yields 4 moles of ATP per mole of glucose. 2 moles of ATP are produced in the glycolysis, which is the reaction from glucose to pyruvate, which is the starting point of most fermentation reactions of glucose. The glycolysis is the first part of the fermentation reaction, and it includes an oxidation step. The glycolysis does not only produce 2 moles of ATP, but also 2 moles of electrons. Like ATP as a currency of energy, microorganisms have a group of molecules called coenzymes that can carry electrons and act as universal reduction and oxidation equivalents. The most common one is nicotinamide adenine dinucleotide, or NAD+. It is positively charged and can take up an electron to become NADH. Other electron carrier molecules are NADP, FAD, ferredoxins. There is more variety in the electron carrier coenzymes than in the phosphate carrier coenzymes. In the second part of the fermentation reaction, pyruvate reacts to acetic acid, H2 and CO2, and in this process the two NADH are regenerated back to NAD+, and additionally 2 more mole of ATP are produced. The regeneration step of NAD+ to NADH is mandatory for all fermentation reactions, but not all fermentation reactions create additional energy in the form of ATP. The ADM1 model refers to the reaction converting glucose into acetic acid, hydrogen, and carbon dioxide as mixed acid fermentation. However, this terminology is somewhat misleading. In microbiophysiology, mixed acid fermentation typically describes the metabolic activity of facultative anaerobes such as E. coli, which produce a mixture of end products including acetic, formic, lactic, and succinic acids, along with ethanol, CO2, and H2. In contrast, the ADM1 pathway produces only acetic acid, H2, and CO2. The reason why it is called mixed acid fermentation lies in the term mixed. Unlike in ethanolic or lactic acid fermentation, this fermentation is not a linear reaction route, but a mixture of 2 parallel fermentation reactions after the glycolysis. The pathway proceeds as follows. Glucose is metabolized via glycolysis to yield 2 pyruvate, 2 ATP, and 2 NADH. Each pyruvate is then oxidatively decarboxylated to acetyl-CoA and CO2, generating reduced ferredoxin. The acetyl-CoA is converted to acetate, generating additional ATP through substrate-level phosphorylation. To maintain the redox balance, the 2 NADH from glycolysis and the 2 reduced ferredoxins from pyruvate oxidation are oxidized by a hydrogenase enzyme, which reduces protons to form 4 moles of hydrogen gas. Anyhow, the monosaccharides are converted by sugar degraders to acetic acid, hydrogen, CO2, and more sugar degraders. The growth of sugar degraders requires a nitrogen source, which is inorganic nitrogen. In the ADM1, the terms inorganic carbon and inorganic nitrogen are used. They comprise all forms of CO2, such as gaseous and dissolved CO2, carbonic acid, bicarbonate and carbonate, and all forms of nitrogen, such as gaseous and dissolved ammonia and ammonium. Organic acids are referred to as their salt forms. For example, total acetate is the sum of acetate and acetic acid. The next favorable reaction is the butyric acid fermentation, yielding butyric acid, CO2, hydrogen, and 3 mol ATP per glucose. This reaction is in the ADM1 as well. The next 2 reactions are the lactic acid fermentation and ethanolic fermentation, which only generate 2 moles of ATP per glucose. Ethanol is not an acid and can be produced in low pH environment, for example by yeasts at pH 5. In this environment, volatile fatty acids are in their bioavailable uncharged form. Their pKa value is 4.75 to 4.9, and the acids become toxic and start to have an impact on the free energy of reaction. Lactic acid is similar in some regards, as it has a pKa of 3.9. Lactic acid bacteria can keep up producing acids in low pH environments longer than, for example, acetic acid produces. A typical biogas reactor does not operate at low pH, and these reactions are not common in steady-state stable operation, and therefore are not included in the ADM1. I just put them here to highlight the ATP ranking. The propionic acid fermentation has the following form in the ADM1. 3 glucose react to 4 propionic acid, 2 acetic acid, 2 CO2, 2 water, and 4 ATP. the ATP yield per glucose is lower than in the ethanolic and lactic acid fermentation. In reality, propionic acid is mostly formed during secondary fermentation reactions, for example from lactic acid. So, for example, when the pH in the digester is low, lactic acid fermentation is favorable, and as a next step, propionic acid is formed from lactic acid. The ATP yield is around 2.5 moles of ATP per mole of glucose for the combined two fermentations. There are more than 100 known fermentation reactions starting from glucose, but the ADM1 only focuses on the mixed acid, butyric acid, and propionic acid fermentation. These reactions yield the most ATP per mole glucose, and microorganisms using these metabolic pathways will generate more energy. A high energy yield goes hand in hand with a high biomass yield, meaning more microbial biomass is produced per mole of glucose consumed. The microorganisms using energy-efficient pathways will outcompete those using exotic pathways with low energy yields. So why even bother with butyric acid and propionic acid fermentation and not use mixed acid fermentation exclusively? Microorganisms control the usage of metabolic pathways through mechanisms called induction and repression. They will use the most efficient pathway first. Only when the substrate concentration is high and the most energy-efficient pathway operates at full capacity, less energy-efficient pathways will be activated. Ethanolic and lactic acid fermentation pathways are quite short. Pyruvate can be directly reduced to lactic acid in a single step, regenerating NADH back to NAD+. In ethanolic fermentation, pyruvate gets decarboxylated to acetaldehyde, which is reduced to ethanol, regenerating the NADH. These high-flux, low-yield pathways are kinetically favored and activated if there is enough substrate available. When are substrate concentrations high? They are high when the growth rate is high. Growth rate increases during feed shocks or at low residence times. Feed shocks can be created by sudden feed pulses or by dissolving a crust when mixing is changed. Feed shocks are transient behaviors during which the fermentative bacteria adapt to a new steady state. Another way to increase the growth rate is by reducing the residence time. In the mini-series about microbial growth, I explain how residence time and growth rate are linked in steady-state CSTR. The growth rate is the dilution rate, which is 1 over the residence time. In steady state, microorganisms double with the natural logarithm of 2, which is around 70%, times the hydraulic residence time. A typical AD reactor is a steady-state CSTR that operates at around 20 to 40 days residence time. At this residence time, the fermentative bacteria practically hibernate and use only the most energy-efficient pathways, the production of acetic acid, CO2, and hydrogen. The less efficient pathways are only activated when substrate accumulation is induced by feed shocks or hydraulic shocks. Another reason for high substrate concentrations lies in the mixing behavior of biogas plants. I will discuss this in greater detail in my presentation about mixing biogas reactors. When a reactor is mixed, the agitators cannot provide mixing all the way down to atomic level. There will be a lower limit to which scale a reactor can be mixed. This scale depends on the viscosity, density, and volume dissipated power in watts per cubic meter. It is called Kolmogorov microscale, and for a typical biogas reactor, it has a size somewhere between a ping-pong ball and a cabbage. These volumes cannot be mixed by the agitator system of the biogas reactor and are effectively small batch reactors that swim around in a biogas reactor. The totality of all those small batch reactors has a residence time distribution similar to a CSTR. Some of those mini-reactors leave the digester very early and some a lot later than the average residence time. If the reaction is a first-order reaction, the compartmentalized reactor behaves similarly to a CSTR, but for higher reaction orders or complicated reactions like monokinetics, the situation looks different. The Kolmogorov model clearly oversteps its limits in an AD reactor with several days residence time. But the general principle holds. Mixing is not ideal down to microorganism scale, and there are microenvironments in a digester with high substrate concentrations. The next group of biopolymers in the ADM1 is the proteins. In the ADM1, the proteolysis is a first-order reaction. In reality, this reaction is catalyzed by fermentative bacteria producing proteases and peptidases. But in the ADM1, the concentration of fermentative bacteria or amino acid degraders does not impact the reaction. Amino acids differ from monosaccharides in their acetogenic reaction, where the sugar degraders have several different metabolic pathways to choose from, and the fermentation end products are mostly governed by external factors such as pH, hydrogen partial pressure, and availability of metabolic pathways. The breakdown of amino acids occurs mostly through the Stickland reactions. Not all amino acids can react via Stickland reactions, Some amino acids are oxidized using protons or CO2 as electron acceptors. In the Stickland reactions, two amino acids are consumed simultaneously. One amino acid is oxidized and loses a carbon, while the other is reduced and gains a carbon. Both amino acids lose their amino group and become a volatile fatty acid. Some reactions produce or consume hydrogen or produce CO2. The amount of hydrogen, CO2 and acetic, propionic, butyric and valeric acids produced depends on the amino acid composition of the degraded protein and can only be varied slightly. While the fermentation of monosaccharides only produces higher volatile fatty acids under stress, proteins will always ferment to a broad mixture of higher volatile fatty acids. The ADM1 does not include individual Stickland reactions, but simply allocates stoichiometric factors for the reaction of amino acids to amino acid degraders, CO2, volatile fatty acids and hydrogen. The acidogenesis from amino acids is the only source of ammonia in the ADM1. Some ammonia is consumed during the growth of the amino acid degraders. The uptake of amino acids and subsequent acidogenic fermentation is described as a monokinetic with an inhibition term for pH and a limitation term for ammonia. The hydrolysis of lipids follows a first-order reaction in the ADM1. It produces long-chain fatty acids and monosaccharides. The monosaccharides here are the glycerol produced in the deesterification. In reality, the hydrolysis of fats can become mass transport limited at high lipids concentration in the feedstock. Long-chain fatty acids are also an important inhibitor of microorganisms. They can diffuse into the double lipid layer of the cell wall and damage its integrity. But these effects are not considered in the classical ADM1. The acidogenesis of long-chain fatty acids is the beta-oxidation reaction which makes acetic acid and hydrogen. The reaction is a monokinetic with a limitation term for inorganic nitrogen and limitation terms for pH and hydrogen. In the ADM1, long-chain fatty acids do not inhibit this reaction. The next reactions are the syntropic acetogenic reactions. There are two groups of acetogenic reactions, homo and syntropic acetogenic reactions. Homoacetogenic reactions create only acetic acid as product, whereas syntropic acetogens produce acetic acid and hydrogen, or formic acid, and must grow in symbiosis with methanogens that can convert electron carriers like hydrogen to methane. The mini-series about microbial growth has a whole presentation about acetogens and their growth. The ADM1 does not consider homoacetogenic reactions, but focuses on the syntropic acetogenic reactions using propionic, butyric and valeric acid as substrates. Let's start at the top with valeric acid. The reaction in the ADM1 is valeric acid plus 2, water reacts to propionic acid, acetic acid, 2 hydrogen and valerate and butyrate degraders. This group of acetogenic bacteria can consume both butyric and valeric acid. During growth, they bind nitrogen from the inorganic nitrogen or ammonia pool. The valeric acid degradation reaction is a monokinetic with a limitation term for inorganic nitrogen and inhibition terms for pH and hydrogen and a special competitive inhibition term for butyric acid. Butyric acid is converted by the same group of microorganisms to 2-acetic acid and 2 hydrogen. The reaction is a monokinetic with a limitation term for inorganic nitrogen and inhibition terms for pH, hydrogen, and a competitive inhibition term for valeric acid. Propionic acid is converted by propionate degraders to acetic acid, CO2, and 3 hydrogen. This reaction is the most sensitive to hydrogen partial pressure, as we will show later. Because of the high toxicity of propionic acid, it is also quite important to the biogas process. It is less important in the ADM1. This will become clear in the next slide when I talk about Acetoclastic methanogenesis. In the ADM1, the propionate degradation is modeled as a monokinetic with a limitation term for inorganic nitrogen and inhibition terms for pH and hydrogen. The last two reactions cover the methanogenesis. The Acetoclastic methanogenesis is the reaction of acetic acid to CO2 and methane. It is modeled as a monokinetic with a limitation term for inorganic nitrogen and inhibition terms for ammonia and pH. The classic ADM1 does not contain an inhibition term for propionic acid in the Acetoclastic methanogenesis. The Hydrogenotrophic methanogenesis is the reaction of hydrogen and CO2 to methane and water. This reaction is the major hydrogen sink in the AD process and thermodynamically limited by low hydrogen partial pressures. In the ADM1, the reaction is modeled as a monokinetic with a limitation term for inorganic nitrogen and an inhibition term for pH, but no inhibition term for ammonia. The very last step in the ADM1 is the biomass decay. All microbial biomass decays following a first-order reaction and reacts back to composite. The idea is that microorganisms will become feedstock themselves when they die and autolyse. The ADM1 suggests half-life times of 35 to 70 days for bacterial biomass. Here is an overview of the ADM1 stoichiometry matrix. The first column shows the 19 reactions, the first row shows the 24 species. The matrix contains only plus or minus, meaning that the species is either consumed or produced. The CO2 or inorganic carbon column shows only negative terms because of the way the C balance is defined. Whether CO2 is produced or consumed depends on the stoichiometry of the reaction. The last column shows the reaction rate. It is either a first-order kinetic or a monokinetic expanded by inhibition and limitation terms. Before I conclude, I want to highlight the role of acetic acid and hydrogen-dependent reactions. These species are involved in all reactions from acidogenesis to methanogenesis. They are both adducts and products, and their activities have a strong impact on many reactions in the AD process. We start with hydrogen-dependent reactions. They play a role in the growth of all three types of microorganisms: acidogens, acetogens, and methanogens. The accumulation of hydrogen will increase the free energy of reaction of hydrogen producing reactions, slowing down and eventually stopping those reactions when they become endogonic. For each hydrogen-dependent reaction in the ADM1, we can calculate the free energy of reaction as a function of the hydrogen partial pressure. I explained the calculations in detail in the presentation 6.4 about acetogenesis in the mini-series about microbial growth. Here is the graph. It shows the free energy of reaction over the decadic logarithm of the hydrogen partial pressure in bar. The conditions are a concentration of 1 gram per liter for all reaction products and adducts, pH 7, 50% methane and 50% CO2 in the gas phase, 37 degrees Celsius, 1 bar headspace pressure, and equilibrium conditions. A reaction can only occur if the free energy of reaction is smaller than 0. In the lower part of the graph, we see the acidogenic reactions from glucose. Those all have a very low free energy, somewhere in the region of minus 300 to minus 500 kJ per mole, and are unaffected by the hydrogen pressure. The syntropic acetogenic reactions have a much higher free energy of reaction and can become endogonic at high hydrogen partial pressures. Without these reactions, longer volatile fatty acids would accumulate in the reactor and eventually cause acidification. The hydrogenotrophic methanogenic reaction uses hydrogen as an adduct. It has a negative slope, meaning that the lower the hydrogen partial pressure, the more negative the free energy of reaction will become. For reference, I also show the Acetoclastic methanogenesis, which does not depend on the hydrogen partial pressure. The essential message from this slide is that the hydrogen partial pressure has to be kept restricted to a tight window, the thermodynamic hydrogen window, in which all reactions can run simultaneously. A healthy biocyanose in the AD reactor will self-regulate the hydrogen partial pressure to this window. But if hydrogen accumulates, this self-stabilizing system is broken, and the reaction from biopolymers to biogas will stop. We can do the same analysis for acetic acid. Here are all acetic acid-dependent reactions in the ADM1. Acetic acid is produced or consumed by all three groups of microorganisms in the biogas reactor. When acids accumulate, the pH will start to drop, which shifts the dissociation equilibrium towards the bioactive uncharged acid form. Similar to the thermodynamic hydrogen window, we can plot the free energy of reaction as a function of pH instead of a function of hydrogen partial pressure. This graph is for a concentration of 5 grams per liter for all involved species, 50% methane, 50% CO2 and 10 to the power of minus 4 bar hydrogen in the gas phase. The headspace pressure is 1 bar. The temperature is 37 degrees Celsius. The ordinate shows the free energy of reaction in kilojoules per mole. The abscissa is the pH value. I focus only on the region from plus 20 to minus 50 kilojoules per mole. The acidogenic reactions have lower free energies and are uncritical and not shown. While the propionic acid oxidation does barely depend on the pH value, 1 molecule of propionic acid reacts to 1 molecule of acetic acid, and propionic and acetic acid have similar dissociation constants, the oxidation of valeric and butyric acid, and in fact all beta-oxidation reactions becomes endogonic at lower pH values. The reason for this is that one acid reacts to two acids, which makes these reactions sensitive to low pH. This dependence is the reason why longer chain fatty acids and not just acetic acid accumulate in a digester acidification. At low pH, the higher volatile fatty acids are no longer oxidized to acetic acid. The Acetoclastic methanogenesis is exergonic at all pH values, but a low pH inhibits the methanogens as they can no longer maintain a proton gradient over the cell wall. This so-called proton motive force is the main source of energy generation for methanogens. So the ADM1 explains very well how a digester can acidify and how the accumulation of hydrogen or volatile fatty acids stop the conversion from biopolymers to biogas. So, what are the strengths and weaknesses of the ADM1? Let's start with the strengths. The model itself is rigorously structured. Its core is a matrix of 24 species and 19 reactions with clearly defined reaction rates. The species are balanced in COD, carbon or nitrogen, which is an elegant way to avoid modeling water incorporation in the reactions. The ADM1 can easily be expanded or modified. For example, if we want to include propionic acid toxicity into the kinetic of the acetoclastic methanogens, or convert first-order reactions into second-order reactions, we only have to modify the rate term. The ADM1 also suggests a couple of alternative inhibition and limitation kinetics. It is also possible to introduce new species, for example to distinguish between starch and cellulose. The ADM1 covers all 4 stages of the biogas process and their interaction. It is more comprehensive than a simple first-order reaction. The ADM1 can be used to model an acidification and can explain why an acidification stops the formation of biogas. The model is entirely kinetics-based. It does not calculate free energies or prioritizes certain metabolic pathways. In the classic ADM1, the pathways are defined with the stoichiometric coefficient matrix, but it is also possible to define dynamic rules for stoichiometric coefficients. The original publication of the ADM1 does not only describe the model, but it also discusses the limitations of the model. For example, alternative fermentation reactions from sugars, sulfate reduction and sulfide inhibition, nitrate reduction, weak acid and base inhibition, long-chain fatty acid inhibition, acetate oxidation, homoacidogenesis, and solid precipitation. It also explains mass transfer and solving the model for a CSTR. The main weakness of the ADM1 is its complexity, even though it has been restricted to just a few reactions. The model has 24 species and 19 reactions which are modeled as differential equations. Additionally, there are algebraic equations for mass transport and pH calculation. This requires a differential algebraic equation or DAE solver. Many of the species are not normally measured. For example, it is difficult to quantify the reaction parameters for the reaction chain of composite to carbohydrates to sugar to volatile fatty acids if carbohydrates and sugar are not measured. The first reaction step, disintegration, could be very fast, while the second step, carbohydrates hydrolysis, could be very slow, or vice versa. It is impossible to tell if the intermediates are not measured. Additionally, volatile fatty acids can also be produced from hydrolysis of proteins. If we only measure composite and VFA, it is very difficult to find the correct model parameters. And because the intermediate products are also immediately consumed, they are only present in low concentrations, which means measurement errors have a high impact on the parameter fit. And there are many parameters to fit. The original model contains 18 stoichiometric factors, plus some that are hard-coded into the equations. Additionally, there are 38 kinetic parameters, plus parameters for the algebraic equation system, mass transport coefficients, and concentrations of strong anion and cations. To fit all those parameters properly, the system must be operated under different residence times and substrate concentrations, exposed to shocks and dynamic changes, while we hope that those changes will not cause second-order effects in the stoichiometry matrix. It is not possible to fit all 56 parameters from one steady-state observation, or more precisely, it is possible, but the resulting parameter fit is useless. The ADM1 should not be used for reactor control or predictions. For this application, it makes more sense to use a simpler model with fewer parameters, but change those parameters using an observer or estimator. The ADM1 is unobservable because it would require the measurement of many independent species. The gravest danger that the ADM1 poses is that people get very excited about complicated maths. If it looks complicated, it must be true. This is scientism and not science. If you hear phrases like digital twin, run. Researchers can go to great lengths to model small details like the concentration of valeric acid in the reactor, but completely overlook the impact of macro and micromixing, residence time distributions, the pH and hydrogen partial pressure gradient over the digester height, the existence of a post-digester, and hundreds of other factors that impact the feedstock conversion. When a plant is not performing, visit the site for troubleshooting rather than play around with the ADM1 to look for explanations. In my opinion, the ADM1 is an excellent model for academic and educational purposes. It describes all the interconnections and the symbiosis between the different phases in the biogas process. A good understanding of the ADM1 will prevent design errors in biogas plants. It should also be mentioned that the ADM stood the test of time. Unlike its sister model for the aerobic process, the aerobic sludge model or ASM, the ADM is still at revision 1, 25 years after its publication. This concludes the presentation about the ADM1 model. I hope you have learned something new, and I see you in the next presentation of Biogas Basics.